Okay, good morning, everyone. How did the homework go? Any questions? Okay, I'll give you a few more minutes of everybody to join in. And please put your question on chat if you have any. $35, okay. And it's anybody beside Aaron. I want all of you to pitch in. Okay, we start. The answers to your exams is on Brightspace, so please start the review for those who didn't, and you have the answer there. And remember, I have office hours, so you guys feel free to show up. Okay. So I look at number 35. Oh, okay. So yesterday we saw the arc length. It means that if you have the graph of a function, okay, and what we are interested in is basically what's the length of this curve. So in the length, the formula for it was a simple formula. I mean, not simple, but so it's the integral from a to b of the square root of 1 plus the derivative square dx. And if you remember how we did it, we kind of broke this into little line segment. We found the length of every line segment, which was almost the square root of 1 plus the derivative times the little delta x. Delta x is from here to here. That's delta x. And then we added those lengths. Okay. So now let's look at what 35 is about. So they give us the following. They give us the following integral. Integral from a to b of the square root of 1 plus 16 x4 dx. Okay. So they gave us the integral, and the question is, what function have arc length? What's given inside the integral? So they give us the integral, and they want us to ask us, what is the function whose arc length is given by this integral? So that basically wants you to go backward. All right, ideas? So which function should go in here to end up with this integral? It's not very hard. Anyone?
What did you say again? Or ask?
You should do the homework, Ebuka. The question is, this is the integral, and this integral represents the length of the graph of a certain function. What is the function? So they gave you the length. The question is, what the function that should go in here?
4x squared?
What?
4x squared?
4x squared. Yes. So what is the function? It means this piece here This is 16x to the 4. Correct? It means what is f? So they're just making q. It means f prime is 4x squared. Actually, f prime is, okay, let us take the positive root, 4x squared. It means, what is f? So what is f? So now you have f prime. So what's f going to be? Quickly. What you have here is the derivative, not the function. So what is the function? The function is, you have the derivative, the function is the antiderivative. It means f of x is 4/3 x cubed, not only 1 plus a constant c. So you can have 4/3 x cubed plus 1, 4x x cubed plus 2, and so on and so forth. So that's what's going to be the function. So that gave you the derivative, and the question is what the function. So the derivative square is 16x4, so f prime is 4x squared, but I want f. It means I need the antiderivative, which is 4/3 x cubed. That was just making you think a little bit backward. So B is the same question. It's 1 plus 36 cosine squared to x. Okay. And the question is the same. What is f? We can think backward again. This piece is the derivative square. Means f prime is 6 cosine to x. That's the derivative. So what is the function f? F is going to be the antiderivative of this function. Then now the job is to find the antiderivative. It means 6 antiderivative of cosine to x dx. Now to find this, I need a little bit of substitution. And this would give me 6 times integral of cosine u, the dx is half du. So this would give me 3 sine u plus c. It means 3 sine 2x plus 4. So these are the function. And now if I find the derivative of this, I get 6 cosine 2x, and this would give me the arc length. So I just want you to go a little bit backward in those formulas. Any other questions from the homework before I proceed? Please make sure you're doing them. Please do the homework. There is no way out. Can you go over number 11, Aiden? 11. Okay, we go number 11. All right, so we have the following function, y equal 1/3 x to the power 3 half on the interval 0, 60. Okay, so we have a x equal, so we have this function here, and this is 60, and we want to find the length of this curve from here to here. So if you move from here to here, how much was the distance you've traveled? All right, so to apply to find the arc length, I need the derivative, step number 1. So it's a third times 3 half times x to the 3 half minus 1, a half. So this would leave me with a half x to the half. Please, if I do any mistake when I'm computing, just stay with me. So the arc length is going to be the integral from 0 to 60 of the square root of 1 plus the derivative squared. So which will give me the integral from 0 to 60 of 1 plus A half times x to the power a half square, it means a half x to the power a half. You multiply it by itself, you get a fourth. X to the half times x to the half is that. So it's pretty much like very similar to the one I did yesterday. So my u, because as I said, those integrals are very hard, so the number of problems are quite limited. Du is 1 over 4 dx. So this would give me the integral of square root of u times dx is for du. Now the limit. As I said several times, you can change the limit immediate at the beginning, or you can wait to the end. You have a choice. So let us see. The limit here are easy because if x is 0, u is 1. No problem. If x is 60, so let us do that. X is 0, u is 1. If x is 60, then u is 1 plus 1 over 4 times 60, which is going to give me 1 plus, that's 15, I think, which is equal to 60. So this would become integral from 1 to 16 of that. And now the rest is a simple integral. U to the power a half du. It means 4 times 1 over a half plus 1. We've done this several times by now. Between 1 and 60. And the rest you evaluate. Okay? All right. Okay, today we're gonna move. So those sections before the exam, I usually do the section which mainly requires you to be able to apply the formula instead of deriving it like what we did before. So today we're gonna start section 6.6, surface area. So basically, what's the surface area? The surface area is basically, so in 3D, it means if you have a solid not in the plane, but in 3D. So the surface area is basically the area of the outer layer. It's the area of the outer layer of the object. It's solid. Okay, so that's what the surface area. So we are in R3 now, or basically in 3D. You have a solid, so the surface area is the area of the outer piece. So very simple example. So if we have a cylinder, because these are the easy stuff we can work with. If we have a cylinder that's not a shell, there is no thickness here, just a cylinder. So what's the surface area of a cylinder? It means if you take the cylinder, you open it up. That's really what the surface area is. It means the area of the outer piece. It means if you take it and you open it, take a cylinder, open it, you get really a rectangle. We've seen this picture before. That's honest to goodness rectangle. Then the surface area of the cylinder is basically the area of the rectangle. That's really area of the rectangle. Okay, that's really what the surface area is. So if this is R here, and this is H, is when you open it, this is gonna be H, and this is gonna be the circumference of the circle, 2 pi r. So this will be 2 pi r times H. Okay, and since whenever we have area, we cannot have R square H, because R square H will imply a volume. So it's RH. So that's really what the surface area is. You open the object and you measure it. You see what the area is. So if you have a cone, okay, and you open it, what do you think you get when you open a cone? Anybody? You take a cone and you open it, what do you get? You know, can you imagine what you open the cone, what you get? You get something like this. You get that when you open it. So the surface area of the cone is basically the area of the sector. We call this a sector of the sector. So that's really what the idea of a surface area. It means you have a solid, you open it up and you see what the area of the outer layer is about. Now what we are interested in this section is the following. Okay. What we're interested in is that. Suppose we have the surface area of solid of revolution. Of solid of revolution. Okay, that's the idea. Suppose we have the graph of a function, only the graph of a function between A and B. Okay. In previous section, what we did is the following. We took the region below the graph and we rotated it about the x-axis. So we rotated the whole thing. This was full. And we rotated, we got a solid, which is totally full inside. Now we're not going to rotate the inside region. That's not the one I'm interested in. We're only going to rotate the curve itself. That's what we are going to rotate. So when we rotate this curve, we're going to definitely generate a solid. And the question is, what's the surface area of the solid? So the inside is totally hollow. There is nothing in here. I'm only interested in the surface area of the solid. Because that's really the question. So I'll give you the formula. I'll explain it very roughly, and then we will do problems. So the surface area, that's the formula. The surface area of the solid. So remember, that's an area now. So for you, it's just like you take the solid, cut it, open it, flatten it, you get an area. That's what the surface area is. The surface area of the solid obtained by rotating the graph of a function. We're rotating only the graph. We're not rotating the region. The graph of y equal f of x, where x between a and b is given by this. All right. So the surface area, we usually use SA for the surface area, is equal to, of course, an integral from a to b of 2 pi f of x times the square root of 1 plus the derivative of f squared dx. Okay, so the surface area is given by this formula. Very roughly where the formula comes from, and then we will do an application for that. Okay, so let me explain very, very roughly how this formula came about. You don't have to write because this one, I just want to explain it a little bit. Okay, and I need your help. Right. Everything we do so far to find surface area, to find volume, is to approximate whatever we want by something easier that we can really deal with. And nothing is changing here. So this is what I am rotating. This is my A and this is my B. And finding the surface area is practically very hard. So the way the formula is like that. We do what we did yesterday. We cut this into pieces and we basically rotate every piece. So we rotate every piece right there. So I'm going to take this piece and rotate it. And I rotate this piece, I get something like that. Remember, it's a that's the piece. And the question is, what's the surface area of this piece. So I'm call this like in X. And what's the surface area of this piece? So if I take this piece on the side, and I'm going to cheat a little bit, I get something like that. That's the piece. So almost like a cylinder, like almost like a cylinder, not quite a cylinder, almost like a cylinder. So let's see what's going to be the surface area of that. So the surface area of this is, all right, as I did the cylinder, this is my X. It's the circumference of this circle times the little bit of height, the slanted height a little bit. That's the circumference. Now, what's the circumference of the circle? If this is X, the circumference, the radius here is f of x. So the circumference of the circle would be 2 pi times f of x. That's the circumference of that circle. You times it by this little bit of height in here. But according to what we did yesterday, the height in here is 1 plus the derivative of x squared times the delta x. So that's the height, which is the square root of 1 plus f prime of x squared times the delta x. So in the formula here, where is everything coming from? 2 pi f of x is basically this circumference. This piece here is the length of this piece right there. And what we did is we added them and we got the surface area. So everything is basically by going back to simple stuff and approximating complex object with way simpler object. So that's really how the formula is coming from. So now let us do two applications to that. Simple application. So example number 1 is, right. So find the surface area. The surface area of the solid obtained by rotating the graph of y equal to x for x between 0, no, I don't want 0, for x between 1 and 4 about the x-axis. Okay, first let us draw to see what we get, and then we will find the formula. Okay, so y equal to x, that's y equal to x between 1 and 4. So I'm not interested in that, between 1 and 4. Okay, so that's what I'm gonna rotate, this line right here, that line. Okay, if I rotate this line, what do you think I'm gonna get? If I rotate this line about the x-axis, what do I get? Imagine the picture before I draw it.
A cone?
Uh, Not quite. What kind of cone? Keep thinking.
A 3D cone?
Yes, it is 3D cone, but not a full cone. It's between 1 and 4, all of you. So is it a full cone? What's the name of this picture, you guys? It's like a cone where there's a truncated cone. It's a cone where you cut a little bit at the bottom of it. That's what you're gonna get. So it means you have a piece of the cone which is being cut. Now this has a name. Anybody knows the name of a picture like that? This is a cone, but you cut the bottom piece. Anybody know what name this object have? We call it a frustum. It's just like a cone, but it's a truncated cone, not a full cone. It's a totally a truncated cone. So the question is, what is the surface area of this cone? It means you take this truncated cone, you open it, you see its area, and what's this area of this truncated cone? All right, so the formula tells me that first I need the derivative, which is equal to 2. So the formula tells me that the surface area is the integral from 1 to 4 of 2 pi times f of x. F of x is 2x times the square root of 1 plus the derivative square dx. Okay, so this would be equal to 2 pi. So I have 2 times 2, so it's give me to 4 pi integral from 1 to 4 of x times the square root of 5 dx. The square root of 5, I can take it out, times a half x squared between 1 and 5. I mean, this has really become fairly simple once we use those ideas. So that's what give me 5 squared, 25 divided by 2, minus a half, 24 divided by 2, that's going to give me 12. 12 times 4, 48, pi square root of 5. That would be the surface area of this truncated cone. Okay. One more example, and then we move on to a different idea. So it's really just a formula that you guys have to apply correctly. So example number 2. Again, all right, and this is for the algebra of it. So we're gonna rotate the graph of y equal square root of x for x between 0 and 4 about the x-axis, and find the surface area of the resulting solid. So that's root x, and I'm rotating it. It's not the volume I'm interested in. I'm interested in the surface area. It means, you know, this outer layer. What's the area of the outer layer? All right. So this is my function here. This is square root of x. I need a surface area, so I first need to find the derivative before I plug in anything. So it's a half x to the power minus a half, or 1 over 2 square root of x. Whichever we use, whichever we think is easier for us to work with. So the surface area would be integral from 0 to 4, that's my 4 right here, of 2 pi times f of x times the square root of 1 plus the derivative square dx. So finally, this will be not finally, so it's equal to 2 pi is a constant, only constant can be taken out. And I need to simplify the term under the square root before I go any further. 2 root x multiplied by 2 root x will give me 4x dx. Crucial to do the algebra correct. If you don't, there is no way you can integrate those functions. So now this is 2 pi times. It looks very hard, looks complicated. What do you think? What do you want me to do to be able to manipulate this integral? Any ideas? You guys are too quiet. Okay, if you guys have to deal with that, what do you think? What do you want me to do? Anything? Not supposed. Can we spread? I have have to understand what you mean by that. You can speak up if you want. I don't know. Multiply the root. Distribute. Oh boy. Okay. Multiply the distribute. I don't know what you mean by that, Aaron. I have to understand what you guys mean. I understand, Arian. Multiply the roots. Distribute. What do we mean? Okay. All right. We're gonna multiply the roots because we can. Square root of a times square root of b is the square root of a times b. So this is mathematically, yes, that's correct. That's mathematically correct. So I'm going to put them under the same root because there is no substitution inside here, as you guys see it. Dx, okay? And we're going to simplify the inside. It's a mess. So this would be 2 pi times the integral from 0 to 4 of the square root of x times 1 is x plus x times 1 over 4x is 1 over 4 dx. Problem is practically done at this stage. So once you distribute, you can do it correctly. Okay, because no substitution. I mean, there is no function, its derivative in there. And now the rest is fairly simple. You put u to be that, du is dx, and then I will have 2 pi integral of the square root of u, and the dx is the du. There is really not much into it. And if you change your limit at this stage, you get 4 in here. And here you get 4 plus 1 over 4, which is 17 over 4. And then this will be equal to pi times 2/3 u to the power 3/2. So as you can see, the square root comes up in most of the formula between 17 and 4. And that's the end of it. All right. So finding surface area, it's the formula is there. What's going to be hard about it is really the integration. So that's why all the problems you guys are given, as I said, will be made up so you can work it. Whenever you have square root, integration isn't easy. We're going to spend like quite a bit, a few days to deal with those integrals eventually. Any questions? All right, now we're going to move and do more application to definite integral. And as you can see, the idea is that we have all those physical quantities, whether it's a volume, whether it's area, what's in arc length, we want to find them. And the only way we're able to find them is with basically approximating them by something we know. And we're going to keep along the same lines. So we're going to start section of whatever it is, 6.7. Okay, I'll do part of it before the exam, and the harder part will be after the exam. I will not do the hard part before the exam. So physical application. Application. Okay. So today I will do one application, mass, and tomorrow I will start work. But first, let us talk a little bit about density. Before I talk about that, I'm going to talk about density. Okay. All right, what's the idea of density? Let us suppose you are in 3Ds, you have a ball, and there is some kind of a liquid in the ball. So liquid in the ball. So here you are in 3D. So you have a liquid, some kind of a liquid in here. Then the density is basically the mass per unit of volume. So you are in 3D, so it's the mass per unit of volume. So they always tell you what's the density of the liquid. It means it tells you what's the mass of it per unit of volume, centimeter cube, inch cube, whatever unit they are using. In 2D, of course, we can talk about density, but here you are in 2D. So let us say this is a sheet of metal, some kind of a metal. We cannot put liquid anymore. And then the density here is going to be also the mass per unit of what? Quickly. Per unit of what? So here, per unit of volume, that's per unit of area. Centimeter square, inches square, that's when you are in 3D. And finally, in one dimensional, it means here we talk about what's called linear density. This means the following. Imagine, and that's what you will imagine, that you have a bar, a very thin bar. So this is a bar, very thin bar, very thin, because we're going to assume that we are in 1D. And here the density, so this bar is made out of something, then the density is going to be the mass per unit of length. Okay, so what's the mass of this per unit of per centimeter, per inch, and so on and so forth. So the density, that's the idea of a density. It tells you how much things, what's the mass of stuff per unit, depending the unit of what? In 3D, unit of volume. In 2D, unit of area. And in one dimension, it's going to be the unit of length. So today, because it's calculus 2, basically we work in one dimension. You guys will be working in those later on. So that's really the idea of a density. Now, we're going to talk about mass of one-dimensional object. So mass of one-dimensional object. I'm going to give you two easy scenarios, and you guys will tell me the answer. So scenario number 1. Okay, very easy scenario. Let us say I have a rod, thin bar. So that's a thin bar, very thin bar. And let us say from here to here, let us say it's 20 centimeter for that matter. Okay, and I tell you that the density, I'm just making up stuff, making up numbers. So I tell you the density is 4 gram per centimeter. Okay, what is the mass of this bar? Quickly, what's the mass of the bar? Okay, so the density of the bar is 4 gram per centimeter. I'm asking you what is the mass of the bar? So the bar is 20 centimeter. How would you do it quickly?
4 divided by 20.
Think again. It means, what does it mean? Density is 4 gram per centimeter. It means every centimeter, let us assume, what's the mass of it? 4. 2 centimeter, 2 times 4. 3 centimeter, 3 times 4. So the mass is going to be 4 times 20. You multiply them because the density tells you per 1 centimeter. So it's going to give you 80 gram. And the unit makes sense. The unit of 4 is gram per centimeter. You multiply it by centimeter. Centimeter, centimeter, you're going to be getting grams. All right, so the first thing is, if density is constant, so the density is not changing, then the mass is density times length. So that's, of course, in one dimension because I'm talking about length. All right, so the density, the mass is always the density of the bar, whatever I gave you, you multiply it by the length. That's what the density is about. Okay, scenario number 2. Second scenario. Let us say I have a bar again, 20. But this bar now is made of two different kind of metals. So it's not one kind, it's two different kind. So up to here, right here, you have one metal, and the density here is 4 grams per centimeter. And this piece here I changed, it's a different kind of metal. And this here, the density is different. So the density of this piece is 2 grams per centimeter. So it's two different kind of metals. What is the mass of the bar? Okay, Brooklyn tells me 50, Kim tells me 38. We have to agree. We have to agree. Oops. Okay, who's right then? So what's gonna be the mass? The density is changing. 50, okay? Everybody tell me 50, I think so. This piece here, from here to here, the density is 4 grams, so it's gonna be 5 times 4. That's the mass. It means 20, the mass of this first piece. How about this one? So it's a different metal, so that's heavier, sorry, that's lighter here. So the mass here is going to be the density times the length from here to here, 15. It is 30. So the mass of the bar is going to be the mass of the first piece. You're adding to it the mass of the second piece. So this is going to give me 20 plus 30, which is 50 grams. All right, so if the density is changing and it's not changing a little bit here, if the density starts changing, and then we have to definitely divide the object. This is the density is constant. I find the mass of this little piece and I add to it the mass of the little piece. So scenario number 2 is also a simple, relatively simple scenario. So the bottom line is that the mass is always the density of the object. You multiply it by the length. No matter how small is the length, the mass is density times length. So that's going to be scenario number 3. What do you think is going to be scenario number 3? Since it's calculus. In calculus, we make things change continuously. So scenario number 3 is going to be varying density. It means the density keeps changing. Varying density. So let's see what the setup is. So here, I write the setup and then I will explain and we work it out. So let us say now, suppose we have the following scenario. So we have a thin bar, very thin bar, is represented by an interval, because we want to come up with a formula by an interval AB. And assume that the density is changing continuously. And let us call rho of x, this letter here is pronounced rho. Rho of x is the density at a point x. So the density now changes continuously. So now that's the picture in our mind. So we have here, this is an interval AB. That's an interval AB. And this is my rod. And one way you can a little bit make sense out of it, the density change continuously. It means the density here and at here are different. The density, this point and this point are different. So one way you can think about it, imagine you have a wire and you wrap the wire around this thin bar. And as you wrap in it, you wrap it tighter, 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 tighter. So the density is actually going to start changing because your wire is thicker and thicker and thicker and thicker. So the density is continuously changing because as you're wrapping the wire thicker and thicker and thicker. So you change your density continuously. And the question is, in this scenario, question is, what's the mass of the bar? All right, so in scenario number 2, I gave you two different density. Now the density keeps changing. So how do you think we're going to find the mass of the bar? Ideas? So the density here are not really the same. So how can we deal with this mess? I have no idea. Okay, anybody else? Remember, the only thing we do in this part is do what? We need a function. No, actually we don't. We have it, it's the density that's changing. We need an idea. How are we going to find the mass of this bar? Add up a bunch of little parts. Here we are. That's what we are going to do because that's what we do in this class. What are we going to do is we're going to take this, split it into tiny pieces. That's about all I can do. We're going to split it into pieces. All right, so I'm going to call this x0, x1, x2, etc., a typical one, xi plus 1, and so on. So I'm going to take it and cut it into tiny, tiny, tiny little pieces. And then how we're going to think. If I take this piece, this very tiny piece, very, very small. So divide AB into little pieces. Into an equal subinterval. And delta x is the length of each one of them. The length of each one of them, okay? So this delta x is very small. And this is the assumption I'm going to make. I'm going to say that if delta x is very, very tiny, I'm going to assume that the density over this little interval is not changing a lot. I cannot say the density all over is not changing because it is. But if delta x is very, very small, I can assume that the mass of this little piece here, the density is not changing. It's going to be the density at any point in the interval. So like I can take it's the density at x0 times the length of this interval, which is the delta x. So the way we're going to do it is if delta x is very, very small, which is that is very small, we can assume that the density does not change. So density is constant on each subinterval or on a typical subinterval. On the subinterval xi plus 1. So if delta x is very, very small, we can assume that the density is not changing. So if I take this interval here, xi plus 1, then the mass of this is the density, however, at xi, so whatever heavy is at this point, times the length, which is the delta x. Remember, delta x is the length, and this is the density. So basically, we cut it into pieces, and we assume that on every piece, the density is constant. And we can do that if delta x is very, very small. So the mass is going to be approximated by the little sum of the masses. It's going to be approximated by the density of xi times the length of every piece. And my I goes, it depends where you start, left and right. It doesn't really matter. Delta x is very small. So the mass is approximated by the sums from here to here, plus from here to here. So when delta x become very little, Riemann sum tells me that the mass is going to be given by the integral from A to B of the density times the x. And that will be given us the mass. So if the density is changing, then the mass is the integral of the density times dx. And watch the unit. This one is, let us say, is unit of mass per unit of length. This is, you time it with, this is going to give me gram. So the unit work. So this is a beautiful example of how Riemann sum is actually used. If the mass starts changing, the density changes, we have no control over the object. So we cut it into pieces. And we assume on every little piece, it is constant. I have to assume that. And then I find the mass of every little piece, and I add them up. When I add them up, I get the mass of the whole object. Okay, so the application are very simple. As far as the problems will be simple, what you guys will be doing is using this formula, and I will assign that for tomorrow. But the idea that I really kind of like in this problem is the idea that we don't know how to find something, we split it into pieces that we can really interact with. Okay, all right, questions before I quit, we stop. Now in calculus 3, you will see the same idea, but it's pushed. So you guys will be working with in R2, in 2D, how do you find the mass? And you will be working in 3D, how do you find the mass of an object? We cannot do it in this class because we work with one variable only. So as you move on, you can find the mass of an object in R3. If the density is changing, how do you find the mass? And it will be also the idea of adding little masses. In this class, we have to restrict ourselves to one dimension. Any question before we go on? Okay, please do your homework for tomorrow. Please come to my office hours and work on the review. This week will not be hard at all, I hope. So this may give you enough time to work on your exam. Any questions? Yes, I am definitely hoping that I will be in person next week. I definitely hope so. If anything happens, I will let you know. But as of today, I'm hoping to be back next week. Any other questions? Okay, see you guys tomorrow. And remember, I have office hours after class. Feel free to come. Bye, guys.